Hey class, how's it going? This is Dr. Humpage. I want to talk a little bit today about the the paired samples t-test. The paired samples t-test, what you have is the same sample. They have a pre-test, they have a treatment, and then they have a post-test. That's the main defining feature of a research scenario where you're going to have a paired samples t-test. In our case, we've got, if you recall from the vignette I made about the null and alternative hypothesis, we can imagine a basketball team. They play the winter season. They shoot free throws during the season. I calculate a free throw percentage for each of my 12 players, so 2 through 13 here. And their average was 64%, and they had a standard deviation of about 13%. And then, I hired a coach somewhere in between to coach them for a few weeks on free throw. I hired a free throw guru. And then we played our summer league, and so I used that summer league as the post-test. So I've got some free throw shooting percentages for each player. And then what I did is I took a grand average of that. So the mean score, the mean percentage in the summer league was about 67%. So at a glance, you can see that they improved about 3%. The standard deviations stayed mostly the same. Revisiting our null and alternative hypotheses. So our null hypothesis is that the mean difference between the two scores, pre-test and post-test, or pre-guru and post-free throw guru, is going to be about the same. There's going to be no change. The alternative hypothesis is that there is going to be a change greater than 0. And so, important to note in this particular example, I'm expecting the scores to improve. I'm not just looking at a general difference. I know which way I think would be significant for me, which would be an improvement in scores. And so that is going to translate into a one-tailed test. When I interpret this, I'm going to be looking at one side of the t-distribution, the positive side. So that's what we've got going on at this point. I suppose I could even revise this null hypothesis a little bit, right? Because in a one-tailed test, I would also want to keep in mind the condition where I can't type and talk at the same time, but I could keep in mind the condition where, they actually got worse, and that the mean difference was less than 0. Now, what does less than 0 mean? You can't really have a less than 0 as a difference in real life, but in statistics we can imagine, a difference in the means here that would be maybe not 3 to the positive, but 3 to the negative. So maybe if they shot 61% after all that coaching, that could be a mean less than 0. In purely mathematical terms, it doesn't make a lot of sense in real life, but such is non-alternative hypotheses, right? I was looking at the assignments, and this is one of the things students tend to struggle with, and you get corrective feedback on, because theoretically it's kind of weird to wrap your head around. It doesn't make a ton of sense. And if you think about it, hypothesis testing is kind of a backwards thing, because we're taking a sample, we're estimating a population. We have these theoretical distributions out there, and we're fitting our data to them. So it gets a little weird, but I'm going to try to keep it simple for you. So let's get out of the weeds, and let's run this t-test. So what's really going to go on, in the program itself is it's going to calculate a bunch of mean difference scores for each of the players. And so we can imagine, this person got 13% better, this person got 1% better, this person got 1% better as well. So that's how this is going to be. It's really going to focus on calculating these mean difference scores and then coming up with a stat for that. And that's how it's going to run the t-test. So it's going to look at something different than just the means and just the standard deviations. It's going to focus more on a mean difference score, right? So that's what's happening within the program. I just want to mention that real quick. Okay, Dr. Chris, now we will get out of the weeds. All right, so the first thing we want to think about is our degrees of freedom for a two-sample t-test. A little bit different than a degrees of freedom for a paired sample t-test. I keep screwing that up. We're doing a paired samples t-test here. So for a paired samples t-test, your n, your group number, right, is we have 24 data points. So our big N is 24, but our group number is 12. And again, it's the same 12 in both conditions, but 12 is still the group number. So N is little n is the group number, right? Big N is the overall sample number. Well, here we're using little n. Okay, so little n is 12, because we've got 12 participants, minus 1, which gives us 11. So that's the formula for degrees of freedom for a paired sample t-test. Our alpha level is something that we choose. So we can choose how stringent we want to make the test. Here I'm choosing a 0.05 alpha level, which makes sense for a free throw, free throw stats. It's not life or death. Now if I'm in the medical field and testing like a life-saving drug, maybe I want a 0.01 alpha level. I want to be more stringent in that scenario. Okay, so that's all that is, how stringent the test is. Okay, so we're going to get our probability value, and this is what's going to indicate significance to us. I'm going to hit equal sign. I'm going to hit t dot test. If you watch the two-sample t-test, this is going to look familiar for you. So I'm going to select my first data array. I've got my 12 participants. I'm going to hit comma. So I've got the pre-test in. I'm going to load the post-test now. Okay, so everyone matches up here. I'm going to choose a one-tailed distribution because, again, it's a directional hypothesis. And I'm just looking at one side of the distribution, of the t-distribution. And I'm going to use a paired samples t-test because, again, that's the one I want here. I want to compare the pre and the post, and that I want to look at each individual's difference in their scores. So I load that in, and then I'm going to hit enter. We'll see what we got. So it's pretty low p-value here of 0.38. So that already tells me this is significant because this p-value is lower than the alpha level. We're going to get a critical value here as well. So again, we're going to hit equals. We're going to use the t.inv function. Now this is going to return a left-tailed inverse of the t-distribution. We want the right-tailed, but I'll take the left here and I'll explain why in a minute. So it's going to ask for our probability value or our p-value. Got that loaded. It's going to ask for our degrees of freedom. And that's all I need here. So I'm going to hit enter. It's going to give me on the left a negative 3.24, which is analogous to a 3.24 on the right because the t-distribution is symmetrical. So basically whatever happens on the left is a mirror image on the right. Again, this is one of these theoretical things where you've got to think it through visually, but that's what's going on. So this probability value on the left side of the curve equates to the same t-critical value on the right side of the curve. What is a t-value? Well, or a t-critical value. It's just a measure of how many standard deviations from the mean my observed p-value is on our null hypothesis distribution. And so I've got a picture. I'm going to talk about that for a second. Again, let's think it through just kind of theoretically here. That's the hardest part of inferential stats, is just kind of thinking about what's going on. But let's just suppose our null hypothesis was true. That would mean, despite all the coaching, our players are still shooting the same percentage. And so if this is both the pre-coaching shooting percentages and the post-coaching shooting percentages would all fall on the same distribution. Nothing has changed in this scenario, right? In the alternative, it means that if our alternative hypothesis is true, they actually got better. So the scores would fall into some new theoretical distribution out here, the alternative hypothesis distribution. In our case, right, we got a t-score of what, like 3.2 and a p-value of 0.0038. Let's see if I remember that. All right, so I'm way out here, right? If I measure standard deviations from the mean, I go 1, 2, 3. I am out here pretty far, right? And I've got the area under the curve analogous to my probability value is like a fraction of a percent. You know, it's like the same odds as winning the Powerball. This curve is asymptotic to the axis, so there's always a little bit of space under the red. So I'm out here somewhere. It's a tiny little bit of probability that I'm defining on this null hypothesis curve. And so basically what that means is that the chance of this happening if the null hypothesis is true is very, 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 very tiny, which leads me to believe that, you know, it's probably just true that they got better. And I'm going to reject the null hypothesis because we're so far out. You know, the statistical probability of this happening by chance is very small. The statistical probability of, you know, my treatment not being effective looks pretty small because we're pretty far out on the fringes. So that'll wrap it up. I mean, that's how you do a two-sample, I'm sorry, I keep making the same mistake, a paired sample t-test. I've been staying up late and doing stats. What can I tell you? So that's all you need to know, and these are going to be the big things you want to talk about, right, in your write-up. You're going to be talking about degrees of freedom, the p-value you obtained, you know, how many standard deviations from the mean that p-value was, you know, how does that relate to your null alternative hypothesis? So those are some things that you're building in this statistical analysis report. I hope you enjoyed the video, and you know, again, shoot me questions that you might have with any of this stuff as we move through the course. Thank you.